Today we will listen to a talk from Alastair. He did his PhD in Leicester and then went on to Cambridge and then Durham. And all the time he has been working on clusters in many different wave bands. And yeah, today he will tell us about the dust and molecular gas in brightest cluster galaxies. So enjoy the talk.
Okay, so hopefully I'm being heard in there. Yes, very nice to be here for the record. So I'm going to be telling you about central cluster galaxies, and my motivation comes largely from X-ray observations, from my history, but using a number of multi-wavelength traces of the properties in the central cluster galaxies. And why, in particular, would I be interested in doing that? If I can get clicker to work. I think it's my laptop has spent so long trying to get started that it's turning itself off. Let me try again. Right. No, that's just from a small window. Too good to be true. Yes. No. Yeah, change the settings and it will bite you. Yeah. 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 Right. So I can now start my talk. Apologies. So I'm going to just give you a very brief summary of the wider context of cold gas in particular, but cold dust as well, in cluster cores, and I'll explain why cluster cores. X-ray selected clusters give you a uniform distribution of clusters irrespective of their overall properties, largely because you're dominated by the extended X-ray emission. And if you're studying the central galaxy, that larger X-ray gas does not depend on the orientation or any jet direction for your central galaxy. So you get a random distribution that's not specially preferred or has any special preferences other than the standard statistics of the central galaxies, and that's a complete sample. And the brightest cluster galaxies are the largest galaxies within those clusters and anywhere else in the universe. So we're studying a relatively rare subset of galaxies, but they have properties which we can use to as an analogy in many other aspects, and I'll hopefully get that across as we go. And in the context of AGN feedback, there is a standard model. If I can use the clicker here just to illustrate. It's going to work. So you have a galaxy which has cold gas in blue and stars surrounding it with some nuclear black hole in the center, which is fueled by the cold gas as it falls in. As the gas, which is cold and baryonic, coalesces and forms a disk in the center, you will start fueling more of the activity, which will then hopefully have an effect on the cold gas, expel it for a while. And in most cases in AGN feedback, the galaxy continues from that point with very little gas. But in cluster cores, we have a lot of hot X-ray gas, which is cooling, and that refreshes this cold gas component that is constantly raining in. So I think my analogy is I grew up in Scotland, and I'm used to constant drizzle. And this is what you have in cluster cores. There's constantly raining gas in this center, which is replenished. If I can get still not got the pointer, but you start at the top, and you're in this constant loop of gas coming in and renewing AGN activity, which may for a while curtail the activity, but it will continue. And there's a constant supply of gas. It doesn't seem to. And you get activity which is more spectacular. You have a larger mass black hole. You will end up with large radio jets, which mechanically can remove large amounts of material and shift it around. So there are an issue of semantics. Cooling flows have had a very bad press over the years. People call them cool cores. Whether it's cooling, whether it's cold, whether it's I've not got the clicker to work at all now. It doesn't necessarily matter for what I'm interested in, just that there is some gas that has cooled. The X-ray gas will reach a point at which it recombines. We know its X-ray cooling time is much less than 10 to the 9 years, in some cases less than 10 to the 8 years. They're really cool centers of massive clusters. So gas must be recombining at some stage. The amount is an issue, but there is some. And those properties are the ones that we're interested in. And understanding individual clusters by looking at one exceptional object is always a way to madness in astronomy. So we're going to try and make sure that we are looking at a large sample of objects with many potentially important archetypes. But I will make one exception at the beginning of this talk, and that is entity 1275, which is the center of, at the center of Brightest Cluster Galaxy at the center of the Perseus cluster, which is the most nearby X-ray brightest cluster in the sky, and has a lot of very peculiar properties. So this is an optical image of it. Let's see if I can get the clicker to work at all. No. Yeah, I'll keep holding it. Yeah, here. So you have the galaxy, an active core in the center, which has a very bright radio source, which is variable, and has a C-foot nucleus. But you also see in red here optical line filaments, which stretch out very large distances, 30 to 50 kiloparsecs from the center, and you also see dust absorption. So this may appear to be a very peculiar elliptical galaxy, but is actually an archetypal central cluster galaxy in a cooling flow system. So it's unlike most giant ellipticals. It has optical filaments, C-foot nucleus, and cold gas, and a bright variable radio source. But in terms of AGN feedback, it's the archetypal object, and the reason why it has 1 million seconds of Chandra time dedicated to it is in order to understand the microphysics of that AGN feedback. So here you can see the X-ray in the grayscale in the background and the radio contours, and there are two very prominent depressions where the hot X-ray gas has been moved away by the non-thermal plasma in the radio, and these cavities continue out, and there are a number of cavities further out that are much, much older, and there appear to be ripples of sound waves of very low notes that push out as you go further and further out in the cluster, which are remnants of mechanical motion at very early, at varying times related to episodes of activity in the central galaxy. If you look at the radio spectrum, so this is the total radio spectrum from the tens of megahertz here through to the far infrared on the right-hand side. And here you see a steep spectrum radio component that dominates below a gigahertz. So this is a 3C radio source. where it's clearly very bright at 178 megahertz, which is where the selection was made. But as you go above a gigahertz, what dominates the radio properties of this source isn't this extended radio emission that you see filling the cavities, but an unresolved variable radio source, which is relatively flat spectrum. This is WMAP data. This source is also detected in Planck and is known to be variable. So a lot of this mess of points here is just because these are taken from NED from many different periods. And I'll attempt to make that obvious. So this is 8, 15, and 5 gigahertz data monitored over a 45-year period. So this is light curve is almost as old as I am. I appeared just about here. So throughout my career, starting in the sort of early 80s, the NGC 1275 has been in decline. This 3C radio source. So it has been declining. It was relatively X-ray bright in the nuclear component at this point and has faded. And in the early 2000s was very quiescent. It wasn't particularly bright X-ray source. It was much quieter in the radio, and there has been no gamma ray radiation. But in the last 5 or 6 years, there's been an increase in the activity in the radio at 15 and 8 gigahertz, hasn't quite caught up at 5 gigahertz, but also in the submillimeter, where this has been monitored as a standard submillimeter pointing source, it has increased quite dramatically, a factor of 4 over the last 5 years in the submillimeter, and it's likely to continue if you look back at the in the radio. It's got, excuse me, it's got quite a way. Wrong button. Press the right button. It's got quite a way to go from this point up to its peak up here. So I predict this will reach a peak at the point at which I have my retirement party in about 15 years' time. So I will enjoy that, and it will continue increasing. And also at the moment, it's a flaring Fermi gamma ray source. So fairly regularly, it brightens. On the space of order a couple of days, it will increase by a factor of 4 or 5. And that flaring activity has got much more frequent over the 5 years of the Fermi satellite lifetime, and its overall average activity is gradually increasing in the same way that submillimeter does. So one important issue with Chandra has been the realization that the cavities you see in NGC 1275 are very common. In virtually every strongly cooling cluster we've seen, there have been cavities detected, and those that don't have cavities either don't appear to be particularly active in their cores, or the projection of these depressions could be aligned along our line of sight, where you don't see a depression in the X-rays. You need to see them at perpendicular in order to see that depression and cavity clearly in the X-ray imaging. So in terms of statistics, these cavities are ubiquitous and very common. And one thing you do have to have, if you've got this feedback, is having very regular and plentiful supply of gas. So one thing that is very important is you need some gas in order to supply that AGN activity. It has to come from somewhere, and you need to account for that directly in order to make models of AGN feedback in cluster cores make sense. So where do we look for that gas, and what properties could it have? So the most obvious place to look is carbon monoxide, which is the standard tracer of cold molecular gas in the universe, and NGC 1275, unsurprisingly, shows it relatively strongly and was detected back in the early 80s, and that was largely put down to it being an active galaxy. No great surprise. Why was it only NGC 1275 that had been detected? There was a period in the mid-1990s where a lot of people spent a lot of time on telescopes looking for carbon monoxide in other systems and never found anything, and gave up in disgust, largely because the detectors in those days, and certainly the receivers, were relatively narrow, the order of 800 kilometers a second wide in velocity, and a lot of the time you didn't know the velocity of the line you're expecting very well, and then if you have a 400 kilometer a second wide Gaussian line, you don't have very much baseline to subtract off. So it's very difficult to detect even if it was there. And also the detectors are based on a telescope the order of 10 to 12 meters. A lot of that isn't large enough to detect enough emission. And also there aren't very many local galaxies known, like NGC 1275 is that extreme. So a lot of the systems that were looked at are much less gas in them when we look back at them now with much better receivers. So it's unsurprising that no one detected anything. So, like all great coincidences, on 15th of February, we knew that there was an asteroid coming, and then one hit us, which was coming from the opposite direction. The same thing occurs in carbon monoxide, that I anticipated getting time, and got time with JCMT to look at a particular object, and once I'd made that detection, then realized that there were a whole lot of other objects with very similar properties, and using the IRAM 30 meter, was able to make a dozen detections within the space of a few months, having realized where I needed to look. So this is just a time series of the number of CO detections made with time. So in the mid-90s, there was one, and then on the Boxing Day, 1998, we made the second one. And then fairly soon after that, we got to about a dozen. And in 2001, I submitted a paper which presented 17 of those detections. And we're now at a point where we have about 46. Slowly, I've been building up the detections, and you can see they jump in units of a few in each observing run. This one I was particularly successful on, where we started looking at objects in the south, where we had a large sample of objects to find. We did very well. And we have detections over a wide range in redshift. And we're now into teenage years. Now, in August, all of my 3 children will be teenagers, so I dread the teenage years. They're very difficult, temperamental, but ultimately very rewarding. So we've gone from 1 to 46 detections of CO. And what can we learn from these detections? Well, first of all, just making detection of at least one tells you that there's some cold molecular gas. So something is cooling or is cold, which is reassuring and needs to be explained. And the fact that in the large fraction of the systems we see much less than you would expect from the classic spherical cow approach of looking at the X-rays and saying how much gas is apparently cooling, which has always been the problem with cooling flows. They predict thousands of solar masses of gas cooling, and you don't see that. And in the X-rays, we're beginning to realize that that's because gas isn't cooling through all the temperatures. It's actually held up at quite high X-ray temperatures and prevented cooling by the AGN feedback. But some gas does cool through the different temperatures. It's just a fraction of that is much, much lower. And actually the constraints on the amount of gas cooling and the amount we expect to be cooling from the best X-ray observations at the moment are about balanced. At least within a factor of 2 or 3, the X-ray predictions of how much gas is cooling below a certain temperature and should become molecular gas is actually comparable to the amounts that we see averaged over a few gigayears. So this has failed me again. It's turned off. I think the battery's died. So I will continue on this. Okay, so what can we learn about the dynamics? So we know from our detections that the range in velocity width that these lines have goes from 100 kilometers a second full width half maximum to 800. So this is a histogram of that full width half maximum of our detections. So we go from 100 kilometers a second on the left-hand side up to 800 kilometers a second. So there's a wide range in velocity width. So you have systems which are narrower than the stellar velocity of the central galaxy, which tells you that they are disk-like systems. And the things which we see as very narrow, the gas interacts, and when we see it face on, we would expect it to have a width which is much narrower than you would expect from the stellar velocity. They don't respond in the same way to the stars. And in systems which we see edge on, we can clearly have very much larger velocity differences in the stars if that disk is large and responding to a circular motion. So we see a number of systems which have multiple components. For instance, here, Hydra A, I'll come back to at the end of the talk, which has a double heat structure in velocity. And if you look at the 0 to 0 intensity velocity width, it's over 1,000 kilometers a second. So there's very dynamical system. So this molecular gas has a scale which is comparable to the velocity dispersion of the central cluster, not just the central galaxy. And again, system ABEL 1664, it's a very similar broad and multi-component velocity velocity structure. So there's clearly something very dynamic going on. And if we look at the line strength, how much CO is there, and compare it to other tracers at other wave bands. Most obvious one is the optical line luminosity, so in a trace from H alpha, which appears to be a ubiquitous tracer of central galaxies in the cores of clusters which are cooling very rapidly from their X-ray observations. And here the blue circles are our detections, and the arrows are upper limits. So the systems here in red are dominated by an active galaxy in the center of the BCG. So we see some extra tracer from the core that there's strong AGN activity in those systems, which appear to lie slightly below the line we're expecting for the amount of carbon monoxide for a given line luminosity. That could be because there's less CO gas, or the line luminosity is slightly boosted. There's an ambiguity. But interestingly, NGC 1275 lies below that line, and so does Cygnus A, which is one of the most powerful local radio galaxies. It has less gas than you would expect from its other tracers, and potentially is telling you that the cold molecular gas has been consumed recently through the AGN activity. And if you look at the Kennicott-Schmidt law in terms of the available surface density of molecular gas against the star formation rate, that ratio is comparable, given assumptions about the size of that gas profile, to local star-forming galaxies. So the physics of star formation in BCGs is very similar to any other collection of cold molecular gas clouds in other galaxies. So we're not seeing anything radically different in star formation. We see some star formation, and it's comparable to the amount you expect for a given amount of gas drawn into a certain size. So what can we do in the future? Well, ALMA will, and currently is, revolutionizing this. We are beginning to get the first observations, and the increase in resolution and being able to trace where that carbon monoxide is in the centers of clusters is going to be revolutionary in actually determining what the dynamics of these systems are. But in the north and at other potential wave bands, Karma in California and Plateau de Bear in France are going to be very important as interferometers that can access the clusters in the north, and the SMA from Hawaii. But also looking at other traces of dense cold molecular gas like HCN and HCO plus are going to be important at understanding not just CO, but the denser traces and how those trace in the cores. But there isn't just molecular gas that we can trace this cold phase of gas in cluster cores. There are atomic lines that are available that at the lowest temperatures actually give you a much better tracer of the potential cooling going on, like carbon-2 and oxygen-1. And Herschel offered a great opportunity to do that, so we were able to get time in the initial stages of open time key projects to observe 11 objects with spectroscopy to look for these key optical atomic traces. And also there have been a number of other open time key projects to do other systems to add to that distribution of objects, not just picking the most obvious traces, but particular targets, but we've got a much larger sample now. And we do detect carbon-2 in every system we looked at, and the statistics on looking at carbon-2 in every system, whether it be at redshift of 0 or redshift of 5, we seem to be seeing carbon-2 everywhere. So it's a good relief, but no great surprise that we see carbon-2. But we also see carbon at the upstream 1 line reasonably strongly, and with the ratio that you expect from most other star-forming systems in these targets that we looked at. And you can also, through the higher velocity resolution that this particular line has, the way that the PAX spectrograph works, potentially see from this particular system potential deviations from from Gaussian line, which appears in the CO line as well. So this is a little movie of NGC 1275 in the carbon-2 line, where we've actually mapped a larger area. So you're seeing roughly the size of the area that you could see from the image that I showed in the background earlier when I introduced NGC 1275. And what you can see that there's a strong carbon-2 line right in the center, but also you see that centroid shifts slightly from the object in the center, moving from right to left. But you also see systems externally, gas clouds of carbon-2 that are seen well beyond the center of the cluster, but have counterparts with carbon monoxide and the H-alpha emission line systems that you can see further out. And they have also a velocity rotation, some shear across them as velocity and position change. So there's something very dynamic, very distributed about this cold molecular gas, cold atomic gas. So what did the Herschel spectroscopy tell us? It tells us that the atomic gas is there. It's a very large potential gas reservoir traced by these atomic lines, and it correlates very well with the CO detections. So the cold atomic and cold molecular gas phases appear to be correlated, at least globally, and the ratio of the lines within the atomic and also to the molecular lines are consistent with all other systems that you see at this sort of far infrared luminosity from ULERGs and LERGs. And the line widths for CO and the atomic lines are very similar, but potentially not completely identical. And the extended emission is consistent with what we see in the other traces. So I've talked about cold molecular gas, cold atomic gas, and where you see those two, you almost always see dust in the universe, and that's exactly the same case in the central cluster galaxies. So where you see this cold molecular gas, you have this pollution of dust within them. So can we use that somewhat easier tracer from far infrared luminosity, far infrared detections to give us an understanding about the cold gas? We made some initial detections in the submillimeter using SCUBA. In the early days when SCUBA was being used to look for lensed background sources in clusters, a sample of about 10 clusters were looked at, and my colleague Ian Smale came up to me and said, well, we've got these detections that are inconveniently in the middle of the cluster that aren't what we're interested in. Are you interested in them? And I jumped with joy and said, oh yes, I'm very interested in these. So we've got a paper out on that detected two. We now got tens, dozens of these detections. But that two combinations of detections, one was very clearly the dust, but the other one was largely built up from the radio continuum extrapolating into the submillimeter. So sometimes the detections aren't what you expect, and they're not dust, but they are in fact the submillimeter, the radio spectrum. And using the mid-infrared as well as the far infrared, we now have detections of the order of 100, if not more, central cluster galaxies, which appear to be relatively bright in the mid and far infrared. Not that in the far infrared these are particularly prominent. So these are three sources with the PAX combination of 70, 100, and 160 micron images, and SPIRE of 250, 350, and 500 in color images. And it's only because we centered these observations correctly that you can actually say, oh, yes, it's the object in the middle that is the central cluster galaxy. They're all detected, but in terms of the contrast to the background, they don't stand out dramatically, which was one of the things that hindered us in the past. And the one on the left-hand side looks much more dramatic when you plot the spectral energy distribution, which is clearly very peaked in the far infrared at 100 microns. There's a radio component on the left-hand side, and the extra peak on the right-hand side is the stellar population. So in this particular system, the amount of energy coming out in the far infrared clearly dominates over the stellar population, which is relatively unusual. This is one of the more extreme systems in terms of its far infrared to optical, but not completely unusual. And if you look at the far infrared luminosity measured for a larger sample from a Herschel dedicated sample, again looking for lensing, but looking at a large X-ray sample of over 50 targets, published by Tim Rawle, who's now working in Madrid in the Herschel Science Center. You make a lot of detections. So the x-axis on this graph is purely from the X-rays, telling you about the central cooling time in the system. So the red hour at the bottom, 1,000 megayears, 1 gig a year, appears to give you a cutoff. Anything which is cooling at less than that rate in the center has a strong far infrared luminosity. Anything which is cooling in the core, in the X-rays, at larger than that rate, you have much less activity in the center in terms of the far infrared luminosity. So there appears to be some direct correlation between the X-ray and the far infrared. So you need to explain why that's the case. It's not just the properties of the central galaxy, it's the properties of the cluster that dictate the far infrared luminosity. And you can also see at the very extreme, you're getting just to a point where they've become ultraluminous at 10 to the 12 solar luminosities in the far infrared. And if you also compare the far infrared luminosity against the H-alpha luminosity, which I showed you earlier, correlates very well with the CO strength, there's a reasonable correlation in those. There may be a few systems on the right-hand side that have much more far infrared for its given apparent H-alpha. The two systems on that far right-hand side appear to be dominated by AGN. So that may be telling us something important, which I'll come back to. And also because this sample was completely unbiased, it looked at a whole large sample of purely X-ray selected clusters. There were a lot of them which didn't have cool core central cluster galaxies, so were upper limits. And if you co-add the upper limits in terms of their overall stellar mass of that central galaxy, you end up with these black upper limits, lower limits for the stellar mass to dust mass. So for the systems which are completely red and dead, there appears to be much less dust for the amount of stars than you see in the most extreme systems observed, which have a lot of molecular gas, and the amount of dust per given stellar mass is much higher. So the systems at the bottom are the ones which are really strong in the optical emission lines and CO. So there doesn't seem to be a possibility that you can create the dust within the central galaxy directly by stellar mass loss, because those should be universal. Stellar mass loss should be the same whether there's star formation or not, just coming from the evolved stellar population. So you can't explain the amount of dust from that explanation. So what do we have? Well, there's one system that stands out that really gives an indication of what's going on, and that's Hydra A, which I mentioned earlier, had this double velocity peak in CO. Again, it's a classic radio source, 3C218 Hydra A. And if you look, we've had a large sample of VIMOS IFU observations. So this is in a paper by Stephen Hamer, who's a PhD of mine, just written up and is now working with Francois Coombs in Paris. So we're working on a paper which includes the VIMOS IFU, Symphony IFU, looking at the optical and near-infrared dynamics of the cold, warm molecular and ionized hydrogen, but also the CO and Herschel data. And this graph, although I can't show you with the clicker, on the top right-hand side, you see the H-alpha flux. So you can see that the H-alpha is strongly dominated in the core and appears to have a flat distribution. And if you look in the bottom left-hand corner at the velocity of that gas, there's a very strong velocity gradient from east to west. And it goes from plus 300 to minus 300. So there's a 600 kilometers a second difference between one side of the disk to the other. And if you look at the orientation of that disk, it's actually perpendicular to the radio jets in the system and the X-ray cavities, which I find very interesting. If you look in the IFU, in the near-infrared with Symphony, where we have much better resolution, slightly smaller field, you see that disk very clearly. It correlates very closely with the center of the galaxy, and the same velocity structure is there, apparent in both the Passion alpha, ionized hydrogen, and the warm molecular hydrogen lines that you see in the near-infrared as well. So this is traced in these. So this is the velocity along that disk axis, and the red line is the same velocity with radius model for every one of these lines. So we have H-alpha traced in the optical, but then Passion alpha and 4 molecular hydrogen lines. Some traced better than others, S1 and S3 being the best traced. And they appear to show the same dynamics. They appear to have what appears to be a disk in this particular system. And if you make a prediction for how much cold molecular gas you'd expect to see on the assumption that each H-alpha or warm molecular parcel of gas gives you a certain amount of cold molecular gas or cold atomic gas, so you trace this velocity structure and then add a parcel to the bottom to give you an averaged single beam emission with velocity. You end up with a slightly asymmetric but double peaked velocity structure, which is what you see in the CO and in the oxygen 1 line with Herschel, which is the one we have the best resolution. So the model that we're predicting is the yellow histogram, and what you see in the red is the CO, and what you see in the blue is the O1. So there appears to be a match between the dynamics traced from the optical and near-infrared into the sub-millimeter and far-infrared lines. And this is the X-ray in grey scale presented, so you can see 2 massive cavities north and south, and the little inset is that rotating disk. So you can see that the axis of the cold molecular material, cold atomic material, is perpendicular to the resulting energy being redistributed from the central massive, the black hole in the center, outwards. So there is some angular momentum coming in, and it does have a memory of what goes on. So what does it mean? So we clearly know that there's a connection between the X-ray cooling and the optical emission lines, paper by Ken Cavagnolo 5 years ago, where, again, you have a property in the center on the x-axis, which is to do with the cooling in the center. Low values imply a short cooling time of this central entropy. And then you have the optical emission lines. You can do this also with the radio power, and it has a very similar dichotomy that above a certain value of this central entropy, there is one system where the central galaxy you detect in H-alpha, and to the left of that, to lower values of that central entropy measured from the X-rays, is something like 95% detection of optical emission lines from the central galaxies. That can't be a coincidence. So there's something about the X-ray properties and the properties in the central galaxy that are linked. So the inference I make, and many of us are making, is that the X-ray cooling is providing that cold molecular gas that fuels the AGN activity and also provides you that H-alpha tracer where you have these cold molecular clouds being irradiated by all sorts of mechanisms in the center of the cluster, but their outer skins will have ionized hydrogen in them, and that's what gives you the H-alpha, and that's why their dynamics are linked quite so closely. And at the moment, the systems where we have a detection of optical lines, but no corresponding CO, is limited mainly by our technology at detecting CO, which is largely gone now that ALMA is in operation. But you can plot the fraction of the detections with a single dish, 30 meter, against the optical line strength of the central galaxy, and you get almost 100% detection at high optical emission lines. And as you get to a sort of particularly low optical line flux, that corresponds to the detection limit of of a single dish, 30 meter. So you start seeing that many fewer of these systems are detected, and you go to the weakest optical line systems, and we see none. And that's all to do with the technology. It's not to do with anything that there's a lack of molecular gas. It's just that the proportion we're expecting is below the current detection limits. Important emphasis on yet. So what we're going to do in the future, so ALMA will clearly allow us to detect substantially fainter systems and resolve them. And also the wide frequency range of multi-wavelength observations that we have available to us now, like WISE to do mid-infrared selection, GALAX to do UV, allows us to look at a much larger sample of clusters and relatively simply go to a particular cluster and say, that has a peculiar central galaxy, let's study that in more detail. So in principle, creaming off the interesting objects is going to be much easier. All we're limited by is the large samples of X-ray clusters or any selective clusters that are available to us. And one crucial example of this is a cluster that only recently came available to us, only recently established that was a cluster, and embarrassingly, this is the most X-ray luminous cluster that we know, at 10 to the 45 ergs per second. It was detected in the All Sky Survey, redshift of 0.6. Embarrassingly, it has an AGN right at the center of it. So the standard assumption is there's an AGN, there's an unresolved X-ray source, it is an AGN. It's only because it was detected by the South Pole Telescope as a Zinniv-Zeldovich effect detection, a very bright one, that anyone went back and said, hold on, let's just check this one. Let's get a Chandra image and look to see what this cluster actually looks like. And it is an X-ray point source, but there is 3 times more X-ray flux coming from the extended emission around it than there is from the AGN. And if you work out directly what the apparent cooling rate is, it's nearly 4,000 solar masses. But if you look at the mid-infrared, the optical, and the UV, and determine what the apparent star formation rate is, it's 800 solar masses a year, which is nearly factors of 3 to 5 larger than any of the others that we've seen. Could this be true? Potentially. Interestingly, it is a far infrared luminosity of 10 to the 13 solar luminosities, so very high. And it also has a dust temperature of 85 Kelvin. So it's very unlike the dust that we see in the other lower far infrared luminosity systems, and appears to have a very obscured AGN in the center of it, potentially of the order of 10 to the 47 ergs per second. Now, that places it in a fairly unique situation within a redshift of 1. There aren't many of these systems at all. And you may notice the bottom left-hand corner, the central galaxy is very blue, because it appears to have either a lot of star formation or AGN activity. And the white rectangle that's plotted on here is what I put in a VLT proposal to do spectropolarimetry for this object, because the other 2 systems within a redshift of 0.6 like this are both known, Cygnus A being one of them and IRAS 0910 being the other, the most powerful IRAS galaxy within a redshift of 0.5. They both have obscured AGN in them with detected polarized broad lines. So this system is almost certainly a similar class as that. So potentially this solar mass, 800 solar mass per year star formation may be overestimated, at least partially, by the fact that it's got a very strong AGN. So the important bottom line is if any X-ray astronomer tells you that they can understand all clusters ubiquitously over every wave band, tell them about this cluster, because it's the most X-ray luminous cluster they should have found and didn't. So as originally an X-ray astronomer, I will be suitably humble. So let me conclude. So hopefully I've got to a point at the end of the talk where you believe that there is a well-established and fairly ubiquitous cold phase in the cores of clusters where there's strong X-ray cooling, which is of the order of 30% of all clusters. And that cooled gas plays an important role in the overall properties of those galaxies. And understanding the dynamics of that cold gas may be a very important way of accessing the important astrophysics of AGN feedback in general, that clusters just have the ability to be able to paint things very big and look at systems which are a large amount of gas falling into a large black hole locally, where we can study these things and they can be applied to similar or lower mass systems at higher redshift, where this same mechanism appears to be much more ubiquitous in the epoch of most massive star formation between redshifts 2 and 4. So hopefully this AGN activity in specialized field can have applications for a wider field of AGN feedback, which is becoming more and more popular. Okay, so thank you.
Yeah, thank you for this very nice talk. Now we have some time for questions.
Yeah, so I was wondering, what are the typical values of the star formation rates that you can derive in these systems?
So they go from a few tenths for the most nearby systems to up to 100, maybe 200 solar masses. Heavily biased towards the lower end. A few solar masses for a canonical few 10 to the 44 cluster is not uncommon. But for the most massive systems, at the extreme end, a few hundred is entirely possible.
So I was wondering, for the least active ones, how much of this could be attributed to, for instance, a return fraction rather than from a cluster-related flow?
Not as much. I mean, clearly, the lower you go, the closer you are going to get to the stellar mass loss rate. But the fact that we, for the systems where we're not detecting any emission lines, that co-added limit on the stellar mass to dust mass was so far away from those which we are detecting, indicates to me that there is an additional supply of gas and dust related to that. But yes, as you get to the very limit, it's always difficult to push over it. But importantly, I think the argument the other way is that if you are going to argue this is all to do with stellar mass loss, you have to explain the other ones. And that's very much more difficult to do. So the argument is not symmetric. I'd argue the fact that you have these systems which are very dusty, very gas-rich, needs to be explained by one mechanism. And if it's true in one case, it should be true in the cases where you're going down to close to the limit. Yes, there may be a border where stellar mass loss and gas cooling give you the same. I can't say for certain, but you have to have two mechanisms. Oh, and the gas cooling from the cluster has to dominate over most of the extreme systems.
Yeah, and just one last question, if I may. Do you have any results for the comparisons between NUV light and H alpha? Are there any? Because you were mentioning.
They're reasonably close. But there is much more of ambiguity in terms of the dust corrections. But in virtually every system where you have reasonably strong H alpha, you see a Galax detection, or at least some HST imaging. But the morphology of that in the UV imaging that's been made of systems with HST, very, very structured, very knotty, and very dominated by the dust obscuration. So you're probably only ever seeing a small fraction of the UV light coming out.
You detect much lower cooling flow rates than previously predicted, or than some people have predicted.
Yep.
I don't know very much about the technical process of cooling flows, but are the velocities likely to be detectable directly?
No. And this is one of the semantic issues that has caused most problems. You say cooling flow, it's more likely a seep. It's a very gradual velocity of the order of meters a second in a system in which there are hundreds of kilometers a second random motions. So the chances of seeing that systematic velocity in comparison to all the other flows and motions is very, very small. So even if you were looking at absorption against that gas, you wouldn't be able to see it. So it is one of those things where your brain hears the word flow and you expect to see a velocity. That's not it is there, but it's just against the background of the other velocities much, much smaller.
So it's a safe prediction that can't be tested.
I'd never say never. I'd like to think in the future, when my grandchildren are at the point at which they can do this, if they wanted to, you might get to a position where you could try to do this, but it's very, very hard.
But it reminds me slightly, but it's more exaggerated form, and more of the flows towards the centers of galaxies, normal flows in plane, where the actual velocities involved are actually reasonably high, but the net rate is much lower because there's flow and counterflow, but it's not the same. It's obviously not the same situation.
Yeah. Nature is complicated, and interesting nature is even more complicated.
What is the typical the time that it takes to cool down? Because I understand that you are, if I understand well, you have first a sort of big X-ray thin gas, which eventually will cool down, but for that you need to, I suppose it's a metallic gas, and therefore the cooling is faster.
So that rate is the order of a gig a year, but the supply of that gas coming back in, just to keep from the pressure balance, keeps that gas replenished. So it's always cooling at a certain rate. So the gas that's in that region that cools at 10 to the 9 years will recombine, but more gas falls in to resupply that. So it won't cool down on 10 to 9 years and stop. There's always a supply of new fuel coming in to cool down. So the time scale is infinite, potentially. It just continues. As long as that gas is still coming in and isn't disrupted by really strong AGN activity or a cluster merger, then that should continue ubiquitously. And that's really what we appear to see in the systems where you have this gas cooling. All of them show AGN activity at some level from their radio core. So it appears to be a reasonably constant.
Yeah, but because the issue is that when you have this gas, X-ray gas, in systems which are not that metallic, to cool down takes a lot of time. Hubble time.
Yes.
All right. So in other galaxies, the X-ray halos will remain as such for a long time. So I assume that because you have metals in this gas, the efficiency in the cooling is higher, and then you can achieve that in shorter time scale.
Yes.
And also, I have a question, which is the topology of this material? Because you have in the cartoons you showed before, you are taking clouds, but obviously when they are X-ray, they are not clouds anymore. They are a diffuse thing, and then when they go back to the pseudo disk or whatever you can call it, I would expect this to be a sort of extended, not cloud-like. So I understand that for that, ALMA observations are going to be the key, because if they would be cloud-like, they could be also the remains of something that were not destroyed and remain in a sort of disk, and then you see them again, and they will share many of the characteristics you have mentioned. I mean, they will not be just things coming back, but things that always remain there.
Yeah, there's certainly cycles, and one of the things that we learned from a very deep observation of Perseus is that there are small inhomogeneities, and there are actually X-rays associated with those optical line filaments. So there appears to be some associated emission, which appears to be re-excitation of cold material. So there are clearly dense clouds in the medium, but within it there are small fluctuations, and it's those that are the seed for cooling. So it may well be that we have the cooling is prompted in sheets or filaments, which is what we end up seeing with these gas filaments. So you have this more extended emission, which is cooling, but that cooling occurs around seed regions. So you can get clumping from apparently relatively uniform distribution through perhaps the seeding being a galaxy moving through, just the wake of the density causing you just a little increase in the density, and that is where the cooling is prompted. So it's very complicated, and you need to go right down to the microphysics. So much more than this talk. Okay.
You mentioned that you have star formation rates of the order of 100 or so in some of the targets. What is the time scale at which you consume the neutral gas at that rate?
Of the order of 10 to the 8 to 10 to the 9 years.
So you should be over in that time scale.
Yes. And the question is how quickly you replenish.
Yeah.
So in the systems where you see of the order of 200 solar masses a year star formation rate, the gas cooling from the X-rays is of the order of that rate. So something leaves the building, but something comes back in as well. So other than what fuels the AGN activity, the budget is potentially gas cooling is directly balancing the budget of
maybe this is very naive, but a part of these star formations never return to the intergalactic medium, simply because you are creating stars, which, I mean, live for as long as the universe. So,
yes. So it has been one of the issues related to the prediction is that if you're going to form stars, then central cluster galaxies should be have a higher stellar mass than you expect. But the total star formation rate over that period is of the order of maybe 20% of the total stellar population. If you average, say, 100 solar masses a year, and it's over 5 gigayears, they're relatively recent. They're not the whole universe timescale. That you don't dominate the stars of the central galaxy from the stars being formed from this mechanism. So you don't see a central galaxy which is 10 times brighter than you predict. It's maybe 30 brighter. And that you can explain. And you don't have to resort to anything unusual, because brightest cluster galaxies are the brightest stellar systems we know. The fact that they're a little bit brighter is no huge surprise. But understanding the stellar population of that would be very interesting. And we're just getting to the point where potentially we have the stellar traces. I was talking to Alex before the talk. Potentially you can use stellar archaeology to understand what the star formation history of the central galaxy is and test this very issue. Yeah.
This is a very short one, actually, or a very long. It all depends on you. It's about how easy it is to estimate star formation rates, because you have this strong emission from the AGNs, and somehow you have to separate the contribution from the AGN and the contribution from stars. Is something clean, or is this something?
No. I think in every area where anyone's attempted to do this, it's as complicated. So it's as complicated as it is in local spiral galaxies. The AGN doesn't necessarily contribute that much in systems like NGC 1275, where we can resolve the AGN contribution locally. We see that very much more extended emission, and we can excise the AGN part from the rest, and that star formation rate is consistent with the wider H alpha luminosity. The issue of whether the AGN activity has much wider effect is an issue, but NC 1275 in terms of the AGN activity is on the extreme edge. Most of the other systems we see some AGN activity, but not nowhere near as large, and there you get very similar numbers. So it sort of indicates that the AGN may contribute, but doesn't contribute the majority. It contributes a fraction. But again, nature is complicated, so, which is why we're here.
Okay, if there's no more questions, let's thank Alastair again. Oh, you can ask it. Okay, thank you.
Sorry.